Hi there. Today we're looking at Fast and Slow Learning of Recurrent Independent Mechanisms by Kanika Madan, Rosemary Nanke, Anirudh Goyal, Bernard Schölkopf, and Joshua Benjo. So this paper on a high level proposes an update to a previous paper which was about recurrent independent mechanisms. And the update it proposes is to learn the individual parameters of the different subsystems that comprise recurrent independent mechanisms at different timescales. The idea behind recurrent independent mechanisms is that you have sub-modules in a reinforcement learning agent that specialize on different subtasks that the agent has to do. And then you have sort of higher level modules, which are attention-based modules, that select those submodules and decide how they communicate with each other. As I said, this paper here builds on that and proposes to learn these higher level parameters at different timescales than the lower level parameters, such that the higher level units can generalize to multiple tasks. And this helps you in environments where you have to do multiple tasks. So we're going to go over this paper, and we're mostly also going to go over what recurrent independent mechanisms are. And as I already said, this paper doesn't introduce recurrent independent mechanisms. That's a previous paper by it has some overlap in authors. So keep this in mind as we go through it. If you're specifically interested in recurrent independent mechanisms, I invite you to go read the previous paper. We'll go over both RIMs and the update to it. In the end, this paper demonstrates that by decoupling the learning, you get benefits in environments where this structure of multitask, multi-objective is given. It can generalize to unseen tasks pretty well. And on the other hand, I think for what this paper does right here, for the fact that it simply proposes this update, I don't think it does enough to demonstrate really that this is something worthwhile, or it doesn't analyze it enough, I feel. And they also call this, what they're doing, meta-learning, which I don't really agree to call this meta-learning, but you'll see for yourself. We'll go over the paper and bear with me. So, as always, if you like content like this, don't hesitate to share it out and tell all your friends about it. And tell me what you think in the comments. They say in the abstract right here, decomposing knowledge into interchangeable pieces promises a generalization advantage when there are changes in distribution. A learning agent interacting with its environment is likely to be faced with situations requiring novel combinations of existing pieces of knowledge. So the hypothesis here is that if you are in an environment that has sort of different tasks inside of it, that where the environment itself changes, so your objective changes as well, then it might be helpful to recombine old knowledge. And the situation you have to have in mind with this paper is one of their core environments here is a sort of a grid world environment. And the grid world environment is simply you have this grid and the agent occupies one cell right here. Maybe the agent is here. And the agent can sort of move around here and do different actions. And there's going to be different things in this environment. So maybe there's like a key right here. This is a key. And maybe there's like a door over here. And the agent will get an instruction. Now, the instruction in this environment might be get the key and go to the door. Then go to the door. Okay, so this might be the instruction. It might actually always be the same instruction in this particular environment, but if you change the key and you change the door where they are, that's already like different tasks. Or it's not the the same environment all the time. You can also vary the size of these environments pretty easily. So all these tasks, these different tasks, they share some underlying structure, which is there's always kind of this world, and there's a key and there's a door, and there might be a wall right here. So they all share this structure. However, what exactly you have to do differs from episode to episode. You can also imagine that there is maybe there's like an orange here. So there's an orange right here. And then the text instruction will say, get or go eat the orange. So now the agent has to ignore the key and the door and go to the orange, right? And additionally, so you can modulate this a lot. Additionally, you can say, okay, the agent maybe only sees its surrounding, maybe like this, right? So the agent only sees whatever is in front of it and a little bit to the side. So it needs to sort of turn around and explore. There's lots of variations. The important thing is that there's an environment that has some kind of overarching structure. And there's different tasks, and each episode is sort of a new task that the agent needs to solve. Now, what happens if the agent here is implemented as in classic reinforcement or deep reinforcement learning as one big box, like one neural network? And then you perform your episodes and you update the neural network, the parameters of the neural network according to your reward. Right? If you solve one task, you will update according to that task, right? So if you solve the key door task, let's call it that, then your neural network, all the parameters will be updated with respect to that task, right? The way you train a neural network is that you change the parameters such that your loss decreases. So you train your neural network to solve that task as well as possible. But now the task changes, right? And all of a sudden it's get the orange. Now all of a sudden this doesn't give you a reward anymore, right? And now the orange gives you a reward. So all the parameters you're going to change in order to serve this new task. Finding the orange. This is supposed to be like a little light speck. I'm terrible at this. I'm absolutely terrible at this. It's like an orange donut. But you get what I mean. This, in general, in the fields of like lifelong learning and multitask learning and so on, this is known as catastrophic forgetting. Catastrophic forgetting. I don't even know why I bother to write. Like no one can read anyway. So there is lots of work in preventing catastrophic forgetting in these types of situations. And the way that this, or the previous paper, the Recurrent Independent Mechanisms, proposed to do that is, let's not implement our agent as one big box. Rather, let's implement it as a collection of like little sub-modules. And these little sub-modules, they focus on individual subtasks. Okay, so a subtask might be find or go to somewhere. Okay, with the somewhere being a parameter that's then taken from the instructions, or maybe one parameter specifically for recognizing the orange. Okay, so now, and the other one is for recognizing the key. Now, if the instructions say go to the key, the module that is recognizing the key might become active, and the module that is for going somewhere might become active, and the combination of the two might then get you to the key. So in each time step, the idea is let's only activate a subpart of these modules, not all of them at the same time. And now only these modules will be active because they are relevant for the current tasks. And then only these modules will receive a learning signal and not the other modules. Okay, the other modules will stay fixed for that particular step in time. And this makes sense if you think about it, right? If your module isn't relevant for the task, then it shouldn't receive a learning update. And that's how you try to prevent catastrophic forgetting. So if this here, this module down here remembers to or can recognize the orange, and right now you're trying to find the key and get to the door, then if you do update that module, it will be in service of the goal of finding the key and getting to the door. So it will forget the orange. However, if you decide, no, this module isn't relevant for the current task, and then you prevent an update to it, then it won't forget the orange. It will only come into life once the task is actually about the orange. And then, of course, you want the learning signal. So that's the idea right here, to prevent catastrophic forgetting. I do have my doubts that is so like that scales to, because the combinatorics of catastrophic forgetting are rather large, and therefore, but depending on how you factor the independent things you need to do, it is a good idea. Okay, so that's the core idea. It is that instead of having this one box, you have a lot of small boxes. And now you do this, right? These reinforcement learning problems, they're often implemented as like recurrent networks. And it's not by chance that this thing is called recurrent independent mechanisms, because each of these little boxes, like the big box would be, is a recurrent neural network. So the way that these things work is that you have your inputs, which is frame by frame by frame, right? And the input goes through some sort of an encoder into a hidden state, and you do have your hidden state that's so the hidden state that the agent itself carries. This is kind of its internal memory. And you use the input frame of the game. So this is frame 1, this is frame 2, this is frame 3. You use the input frame and your own hidden state to produce the next hidden state. And you can easily implement this with some sort of an LSTM, right? And then you use that and that to produce the next hidden state. So that's the normal way of how things are done. Now so that's if you just have like an LSTM controller. Now if you have a recurrent independent mechanism controller, then your hidden state will be sort of it will consist of many hidden states. So the hidden state itself will be a collection of hidden states, right? And so these are supposed to be little vectors. And then the input comes in here, and then only a subset is selected. So maybe this one and this one are selected. Now, the way that this works is, I shouldn't even draw one circle here. I should actually draw 4 circles. Okay. So you have 4 LSTM controllers, and only 2 of them are selected. I'm going to tell you how they're selected in a second. Actually, I'm going to tell you right now. Probably that's better. So what you do is let's do that after. So you select 2, you deactivate the other 2, and the way you produce your next hidden state is simply you copy over the hidden states of the deactivated modules. So you just copy those over. So they remain, and you would update the hidden states of the modules that you selected. So only those modules are active, all right? So now, yeah, so that's that. And there's also a communication step at the end. We'll go into that here, because here's the diagram. So down here you see what I've just told you. This is the system. Okay, you have to imagine there is the last frame right here. There is the next frame down here. The frame and also, so that's the observation and the instruction, they go through some sort of an encoder, which would also be the same encoder up here and down there. Then there is the hidden state, which is here in blue. So these are the independent mechanisms. Wait, that's the wrong blue. So we have, in this case, four independent mechanisms. Those would actually carry over time the state, the internal state of the agent, right? And then at each time step, you have an output of a value head and a policy head. The method they use right here is proximal policy optimization, as far as I understand it. This is a variant on actor-critic method. If you don't know about deep reinforcement learning or proximal policy optimization or actor-critic methods or why we need value and policy heads, I invite you to go look that up. That it's fairly simple. It's very basic algorithm where you can do reinforcement learning. You can calculate a loss, and then you can backpropagate to these either to the encoder and also to the parameters in the recurrent cells here. Okay, so how do we decide which modules are activated and which ones aren't? And that goes through an attention mechanism. And that's what they call here input attention. So input attention is the following. You have your input, okay? And you do have the encoder for the input, which is like maybe some concoction, some alchemic concoction of neural network, right? That gives you a vector, like an embedding of the input. Now, you go to your little modules. Each of them will have a hidden state already, right? And they get to do attention to that input. So the input will emit keys and queries. Now, you can do this in multiple heads, but ultimately, let's do one vector, okay? So here is a key. Sorry, it will emit keys and values, okay? There is a key, and it will also emit the value. We can just do, like, say the value is the input itself if we do not have multiple heads. But ultimately, they emit keys and values, and every single one of the mechanisms emits some sort of a query. So in essence, the input outputs a descriptor for what it contains, right? That's how you have to think about attention. And each of the mechanisms outputs a query for what they would like to see. So they get to look and at their hidden state, and they get to decide what kind of information would I like to read from the input, or what, it's more like a filter. What kind of input is relevant to me? So the mechanism that cares about the orange, it would output probably a query for saying, is there something orangey in the input, either in the instructions or in the picture? Is there like something about an orange there? And the one that cares about the key would obviously say, well, is there something about the key in there? But you can also imagine more abstract things. And then the attention is computed via inner product, and you can see here it's those two mechanisms that are closest in inner product to the key, and then only those two get selected for this particular time step, and those get eliminated. Not eliminated, but only the two on the right get to update the hidden state, as you can see right here. The ones that are not selected, the hidden state is simply carried over, whereas the ones that are selected, they actually get to do computation and update their hidden state. Now, at the end of the update of the hidden state, there is a communication step. So these are not fully independent. They do get to communicate with each other. And so here they have a new hidden state, and here they have the old hidden state. And now we get to communicate with each other. And again, the way this works is that every single one of them processes the input actually. So the input goes through all of them. And all of these emit again a key. All of them emit a vector saying, what did I get out of this input? Even the ones that were not selected, they emit some sort of information. And the ones that were activated, they get to emit a query for what they would like to see of the other modules. And that's how you get the intercommunication, right? That's how you get to like higher order independent mechanisms. So you could actually get a mechanism for going somewhere. And then that mechanism would query sort of another mechanism that says, well, where do I need to go? And the other mechanism that was like, well, I know where to go because the instruction said find an orange, and I'm the orange module, so I located the orange. So they get to communicate to each other. So there's going to be attention-based communication where the active modules read from both the other active modules and the inactive modules. And then you go to the next step and you repeat. And in the next step, it could be that different modules are activated, right? So these two attention mechanisms, the first one called the input attention, that selects the active modules, and then the second one called the communication attention that says how the different modules communicate with each other. Those are sort of the higher level modules that control the flow of information of the lower level modules. And now, in the Recurrent Independent Mechanisms paper, this, as I understand, is just learned end to end. Okay? Now this paper comes into action and says, wait a minute, shouldn't, like, if we have the same environment but different tasks, okay? So here you see individual episodes, and these individual episodes are comprised of a couple of time steps, okay? Now, they say if we want to learn these little modules such that they share knowledge, like they learn the independent things and they can be recombined in different ways across the tasks, shouldn't we sort of, when we learn the individual modules, yes, we do what they call fast update. We do the classic RL where we learn maybe frame by frame or from short sequences within an episode. Okay, so if you know the goal, then let's learn the little pieces that make the goal happen. But in order to learn to select the pieces, you should look across different spans, across different episodes. So that's what they call the slow update right here. So they propose to learn these meta parameters, or what they call them, the communication parameters, in a slower fashion, feeding in longer episodes. And here you can see it even spans across the different tasks. And the idea here is that these slower parameters, they consider longer time spans, they see multiple tasks at the same time, and they learn how to select the different modules depending on the current input, the current task. So by seeing different variants of that in single episodes, they get to know the differences and the commonalities between tasks. Now that is a high goal. So here, my first problem is they call these like meta sequences. And yes, okay, they are meta sequences, but I disagree that is meta learning. So what they ultimately do is, here is algorithm 1. So they randomly initialize the parameters of the attention units, and here the little mechanism units. Okay, they randomly initialize them. By the way, the policy parameters are part of the meta unit parameters, and the value head parameters are then part of the attention parameters. They're not actually part of these modules, but they're learned also on different time scales. Okay, so the policy is learned fast, and the value is learned slow. That's just because feelings. So, while not done, we sample a batch of tasks, and then for each task we sample a trajectory. And then we learn the modules, the mechanisms, in the fashion, right? We keep the attention parameters constant. That doesn't mean we always select the same module. The attention parameters being constant means that the way the queries and the keys are generated from the input, that remains fixed. But it's still going to be differently selected modules from time to time. It's just that the way in which we select which ones are active aren't updated from time step to time step. Right? And keeping that fixed, we learn the individual little things. We learn the mechanisms in a very classic fashion. So you can see right here, these are individual episodes. Okay, the loss function is the proximal policy optimization loss, very classic with like an entropy term and so on. They have it somewhere here. So this is a very classic PPO loss. This thing right here, you have this clipped loss for the policy. You can see here is the so here is you have the probability ratio, which is sort of like the policy parameter. This is the current policy, this is the old policy, and then you have the value function loss, and then you have an entropy parameter loss. So quite a standard loss for reinforcement learning, and you learn that from individual episodes, and you update the parameters of the mechanisms as we said, right? So you only activate the modules that are currently that are selected by the attention, and the backpropagation would reflect that. Then in the second step, you sample again trajectories from tasks, but then instead of keeping the tasks and the episodes separate, you now concatenate all of them into what they call meta sequences, and then you update your attention parameters using those meta sequences while keeping the mechanisms constant, right? So in the first step, you learn, given sort of the activation policy of the mechanisms, how should the mechanisms behave in order to achieve good reward, right? So how they're selected remains constant. So they just get selected, and then they are meant to maximize the reward. And so any mechanism here, when they're selected, they're just being like, okay, what do I need to do to solve the current problem? And if they are selected in a consistent mechanism, that will cause them to specialize, right? If one is always selected when the orange thing is in the input, it will sort of start to specialize in these kinds of tasks. And in the other step, the mechanisms are kept constant, so you have the little submodules that can achieve or can do certain subtasks, and now you're trying to select the best ones of them. So you're trying to train the attention mechanism. How do you facilitate the selection and communication between these given fixed mechanisms such that the reward is the highest? So in this two-step fashion, the little mechanisms get better at the tasks they're tasked with, which causes them to specialize if they're selected correctly. And then the selection itself is updated, which in turn makes the learning signal for the mechanisms better, and then better mechanisms make the learning signal for the selection better, and so on. You can imagine that this two-step process is sort of, swinging itself up, bootstrapping itself up to very, very good interlocking pieces of things. Okay, in the experiments, that looks fairly promising. You can often see, probably you can't see. So the blue one is vanilla, which is sort of an LSTM controller. The green ones is the recurrent independent mechanism one, while the red one, I don't have red here, I have orange. The red one is this new two-step approach. It's not always the case, and reinforcement learning is quite tricky, but this being largely the same authors, I guess they do at least have a good comparison to recurrent independent mechanisms. Though I have to say, this is measured in frames. So how many frames did you consume? And that is an important thing because sample efficiency is important, but also given how complicated this scheme is, I wonder if this is slower or faster than just training both things at the same time, like the recurrent independent mechanisms did. Okay, so again, the difference between this and the last paper is simply that they propose this two-step process where you have one step here and another step here, instead of learning these two things jointly. And they do so deliberately in environments where you have multiple tasks given. So, like it's another lesson in, hey, you need to evaluate on the things where you are really, really meant to be good at. And you need to evaluate in the quantity that you're meant to be good at. I'm not sure if time here would show the same plots if you had like in the x-axis as time or computation or anything like this. It might very well be. So they demonstrate that they do, a lot of have a lot of success with this. They demonstrate that if they train on, let's say, small environments that they call difficult environments, that the metarims, that's their system. The modular is the old paper and vanilla is the base implementation. They demonstrate that even though they all get to fairly good success rate and reward on the difficult problems, if you make it zero shot, more difficult, so you increase the size of the problem without ever having trained on the bigger problem. So you make that room a lot bigger for finding the key. These what they call metarims, they generalize a lot better than the other ones, right? You can see right here, the other ones largely fail, and they claim their system generalizes a lot better. So reinforcement learning experimental results are very, very tricky, right? You've already seen sort of the bars here, the error bars up here, and that's after a long probably experimentation maybe, and also selecting the right metrics and so on. Here we don't even get bars, and here it's quite tricky because not only do, for example, the vanilla ones generalize worse, they also start at a worse point, right? So they start at much less reward, and maybe that's responsible for them not generalizing so well. If you were to actually push, like 0.95 to 0.97 doesn't seem much, but if you look, it's like almost half the error, right? So here, like, if the maximum reward is 1, then this gets 5 less than the maximum reward, and this only gets 3 less. This is quite a reduction. Maybe that's the reason why it zero shot transfers to the more difficult environment. Also here the modular ones, which you have to remember is the exact same architecture as the meta-learned ones. They don't even have a good success in these tasks. So the hypothesis of this paper here is that if you learn all these things at the same time, you will still be subject to catastrophic forgetting in these environments where you have multiple tasks, right? By learning the high-level parameters in a slower way, first of all, in an independent way, second of all, in a way where they see a longer sequences of things, and I do believe also, and this is also a bit unclear, I also do believe they do less update steps. Maybe not. No. I think that it's just that their steps that they consider, the time steps they consider, are 4 times more than the time steps that the learning here considers. So line 6 has some number of steps, n number of steps, and line 9 here considers 4 times n the number of steps. Okay, so they consider longer time scales. If you want some other numbers, they always have 5 of these. So they always have 5, which is what they call little n. And of the 5, there are always k equals 3 active. So there are always 3 of 5 things active at any given point in time. And that is a bit of a different problem I have here. Their contribution is, let's learn these higher level parameters independently and in a more slow fashion. That's the contribution, right? Not the recurrent independent mechanisms, the separation. Now, I would expect there to be a lot more investigation into what exactly this separation and slower learning is doing. They do have some ablations right here, but not many. Most ablations are about the recurrent independent mechanisms itself. So for example, here they compare k equals 3 and 2, and they show, look, across the episode, different modules become active as time progresses, which gives you an indication that yes, in fact, the different modules do specialize in different things, which is cool, right? That is not a property of this separation. That's a property of recurrent independent mechanisms. And here, again, the ablation they do here is different k, so different number of submodules being active. And you can see that if all the modules are active all the time, you have the pink curve, which is quite bad. And if only some modules are active here, like k equals 3, you get a much better performance. Now, I would expect that that you actually try to go to k equals 1 or something like this to show maybe there's an optimal subset and so on. But again, this is a property of recurrent independent mechanisms. Only here, where they say shorter meta episode. So here they say, what if we do the same thing that works well, but we make this meta episode shorter? And then you can see that the curve here, it sort of follows the trajectory of the worst baseline. Now, that is one thing, right? Where they don't say how much shorter they make it. They just say, we make it shorter, and that hurts. I mean, okay. Here they analyze the value function, which is cool. You can sort of see that the value function reacts to different things in the environment. Again, that is not a property of what they're doing. And here, choice of attention, this is ablation, choice of attention parameters as slow parameters. Okay. So they say now, let's do a different thing. Let's actually flip. Let's learn the attention parameters in a fast way and the meta parameters the mechanism parameters in a slow way. And that's what they call meta flip. And here they show that performs worse. Okay, so the top one here is the meta, what they propose, and the bottom one here is the flipped one, where they learn the other parameters slow and the attention parameters fast. And again, okay, that's a thing, right? But it's not so much worse, honestly. And at some point they say, well, it's somewhat worse. And in the text, some they say that is did not perform very well, right here. This did not perform very well. And I disagree a bit. It performed okay. It's certainly better than the vanilla one. It looks like it. Maybe it's the same as the vanilla one. It doesn't seem super duper bad. And I just don't think this is, since this paper is about adding this thing, the addition of this thing and the sort of how much that contributes and what exactly of the thing makes the algorithm stronger, I don't think that's explored enough in this paper. I think too much space is wasted on exploring the value function and which modules are active, which we already know from the recurrent independent mechanisms, right? There are in fact two things going on, right? There is the slowness. There is the fact of, hey, let's learn one set of parameters more slowly than another set of parameters. That's one thing. And the other thing is, hey, let's decouple learning the two parameters. Now, the decoupling actually is what I think makes it not meta. This is simply decoupling. This is not meta-learning as far as I'm concerned. This is not learning to learn or anything like this. It's simply that we have two different things and we learn them at two different times. This is very much like, in the beginning of GANs, you have whatever, your generator and your discriminator. And here you have your data set. And here you have your binary classification. And here you have your latent vector. Okay, this is a basic drawing of a GAN, and what people used to do, at least at the beginning, before we realized how we can stabilize GAN training, is they did these independently. They said, I'm going to do one step, learning the discriminator, and then I'm going to do another step, learning the generator. Instead of updating them both at the same time. And at the beginning, we even did things like, hey, let's learn the generator for 5 steps, and let's learn the discriminator only for 1 step once we get to the discriminator. So it is exactly the same thing. That was not meta-learning. This is simply the fact that if you have a system where the parameters are sort of entangled with each other, like the discriminator depends on the output of another system which itself has parameters. If you change everything at the same time, that can get you into trouble. That can get you into instability. And therefore, it might be a good idea to separate these. And if one system is sort of stronger than the other system, it might also be effective to learn these at different time scales. There's nothing sort of to do with meta-learning, and it's two different things, right? This time scale and the separation are two different things. And these are not entangled here, and they also compare with what they call slow LR. They say, well, in order to compare, what we can also do is we can simply learn the parameters of the attention and the mechanisms at the same time, but we can give the attention simply a lower learning rate. Like we divide instead of dividing the number of steps by 4, we divide the learning rate by 4. And they show that doesn't work. And I mean, it's not a surprise that doesn't work. That is absolutely not the same thing, right? And I'm not even sure what it's supposed to show. I guess it's supposed to show that that you need the separation instead. So the slowness itself isn't a thing, but I don't think even if the slowness was a thing, it is not that you can simply replace the number of steps by a smaller learning rate. Yeah, in any case, but it is at least like some kind of experiment that shows something about the system, right? What I would expect from an experiment like this is, here again, like what the modules are learning, which is cool. Like it's cool that you show, look, this module is learning this one is active when that happens, and so on. And we can ablate the winner modules. So what they do is they take the modules that are selected and then they randomly drop out some of them. And they discover, well, the more we drop out, the less well it works. Wow. But there's no investigation into, okay, what is the effect of learning one thing more slowly? How much is the effect? Can we modulate that? Can we set the number of slow steps equal to 5, to 6, to 10, to 20? Can we discuss how long these meta episodes need to be? Like here it's just like shorter, okay, but there's no indication like how long do they need to be? What's a good length? Then give us like the time penalty that we incur here, not only the frames, right? What's the time penalty? Might there be already something good about simply separating the updates? Like all of this kind of stuff is not really explored in this paper. So again, there is really cool parts about this paper. It makes sense to separate these two because you have an interdependent system. Reinforcement learning is brittle enough already, and it really seems to help against this catastrophic forgetting. However, for the fact that this paper simply adds this two-step approach, I don't think it does enough to show what they're doing and to show the reasons of why what they're doing works. And also I object to this being called meta-learning. So that is my opinion. Please tell me your opinion. This was a bit more ranty than I usually do, but I hope you're still here, and I'll see you next time. Bye-bye.